Each alloy has its own recipe, and there are thousands on the books. Not just steel or aluminum or copper, but hundreds within each of those alloy groups. Welcome to the Manufacturing Show. I'm your host, Chris Carolyn, consultant at Metal Analysis Group. In this podcast series, Masters of PMI, my goal is to help you be successful with positive material identification and truly master your metal testing wherever you may be in the metal supply chain. All the way from scrap metal recycling and metal production at foundries and mills to metal parts fabrication and inspection, PMI testing plays an important role in making sure everyone knows which metal they are working with in order to avoid material mix-ups that can lead to unhappy customers, expensive recalls, or even catastrophic accidents like oil spills, plant explosions, and airplane crashes. We don't like those things, right? So let's get to it. Today we'll be talking about positive material identification. Can't forget about the basics if you truly want to master your craft, so I want to make sure we're all on the same page to start with. First of all, what is it? Basically, the analysis of a material, usually a metallic alloy, to confirm that the material is consistent with what has been selected or specified by the user. You can easily do this by confirming the composition or chemistry of the alloy using techniques like handheld XRF, mobile OES, and handheld LIBS. Each alloy has its own recipe, and there are thousands on the books. Not just steel or aluminum or copper, but hundreds within each of those alloy groups. The unified numbering system for metals and alloys actually keeps track, and it's where you can go. You might see the UNS number attached to some of the metals that you're working with, and that's what it's talking about. So these metal bases, steel, aluminum, copper, are alloyed with alloying elements to add or adjust the properties of the metal. Chromium and nickel for corrosion resistance and oxidation prevention in stainless steel. Molybdenum or moly for hardness and tensile strength in tool steels. Copper is used to increase the strength of aluminum. Beryllium is added to copper to increase its hardness and strength. So why is it important to know which metal that we're working with? As you can imagine, if you were to accidentally use a carbon steel, usually low in these alloying elements, in place of an alloy steel with high temperature resistant properties, in a place with very high temperatures, bad things can happen. Case in point, in 2005, BP in Texas City, a very large refinery, and this was actually 4 months after they had a major explosion killing 15 and injuring 180 people. They had another incident, and there was a major fire causing a reported 30 million in property damage. Luckily, no one was hurt because they were using a maintenance contractor to replace a part in the heat exchanger, and that contractor accidentally used a carbon steel elbow where an alloy steel elbow was needed. So it wasn't as resistant to the temperature and ended up rupturing after only 3 months when it should have lasted much longer. From the report, the recommendation by the Chemical Safety and Hazard Investigation Board, or the CSB, was basically do better PMI. Now expand this to anything built that includes metal. Bridges, buildings, airplanes, automobiles, medical devices, food processing plants. There's metal all around us. PMI testing makes sure all that metal is the right metal to specifications. So basically PMI testing keeps us all safe and healthy. So when do you do it? Basically whenever metal is changing hands in the metal supply chain. So when the foundries are buying scrap from the scrap metal recyclers, they want to test it to make sure it's what they need to make the primary metal. The foundry is then going to give that metal to a parts manufacturer usually. So that parts manufacturer needs to make sure the metal is right for the parts they need to make. Let's say that parts manufacturer is selling its parts to a refinery, or the parts are being used in a refinery. The refinery needs to make sure the parts are to spec so they don't have those major incidents like we discussed earlier. And then the refinery maintenance and inspection. So while parts are in the system, there's generally ongoing maintenance to make sure there's not any parts that are bad or weakening too soon or too fast. Or you often hear the term 100% PMI popping up more and more. That's because originally, generally 10 to 20% used to be accepted. And what do I mean by 10 to 20%? If you have a batch of 1,000 parts, and let's say these are aerospace parts critical to an airplane like engines, you could test 10 to 20% of the batch. So in this case, 1 to 200, and you could call the whole 1,000 parts good. It was PMI'd and identified, and you could send it. Well, now manufacturers like GE, who makes those engines, are requiring the vendors they work with, the parts manufacturers, to do 100% PMI. That means all 1,000 parts get tested to ensure they're the right material before they get to GE, and they're used in critical aerospace parts like engines. Makes sense, right? So how do you do PMI? Well, there's a number of technologies. There's handheld XRF, or X-ray fluorescence. There's mobile OES, optical emission spectroscopy. And there's handheld LIBS, laser-induced breakdown spectroscopy. Generally what all these are doing is they're either using radiation in the case of XRF, a spark in the case of OES, or a laser in the case of handheld libs, to excite or burn the metal to determine the chemistry and the makeup. It'll then use this chemistry to match the material to a grade library in the analyzer. So you use this technology to tell you what the metal is. In most cases, it's impossible to do visually, and there's very few other methods to determine the alloy. So how much does it cost? Like anything else, it can depend on the industry and the urgency or the critical nature of the application. But if you have no equipment or expertise at your job site or within your company, there are many companies available at rates like $300 per hour, plus the cost of getting them on site. Sometimes refineries, when they're doing maintenance or shutdowns, they'll bring in teams of 12-hour shifts to do maintenance as quickly as possible because they want to get back up and running as quickly as possible. So as you can imagine, this can cost on the order of thousands per week or tens of thousands per month. Renting the equipment, on the other hand, if you're comfortable using the equipment and been trained, can cost anywhere from $2,500 to $6,000 per month. Some vendors out there, some rental providers out there will offer daily and weekly rentals to lower the cost if you just need it for a short amount. If you're looking to purchase a handheld analyzer or mobile OES, it's generally about $20,000 to $40,000 for a handheld, or up to $60,000 for a mobile OES. Now, it's important to consider the cost of ownership and maintenance after you make that first purchase. So in recent years, PMI has seen a number of changes, more emphasis on doing PMI, more training available. So I just want to go into a little bit about kind of where it was, where it's come from, and where we are today. First of all, I think globalization has led to a very complex, diverse, and a less confident supply chain. That's why you're starting to hear more and more terms like 100% PMI. You see more accidents, and those help companies, or force companies in some cases, to understand the liability and the risk of not doing PMI. As we get more material and metals from different places around the world, you have to be mindful of counterfeiting of alloys. So as you can imagine, some of those elements that are added into the metals have costs. So if you can put a cheaper alloy in there, or alloying element, it costs you less. And if the person checking it doesn't see, they might pay the consequences. PMI prevents you from suffering those consequences. In the end, it's about quality over profitability. In all these critical industries and critical applications we talked about, quality is clearly more important to avoid some of the disasters we've discussed today. Analyzer performance has also improved. Range of elements has increased. Obviously, we can do lighter elements. There's better sensitivity with the newer analyzers, meaning lower concentrations. Also, we've seen the software greatly increase, making these analyzers easy to use with better data management capabilities. Truly point and shoot. Now, this leads to kind of our last thing I want to focus on as far as where PMI is at, and that is the knowledge and skills gap that such easy-to-use software has kind of created. So the manufacturers of these devices want these devices to be usable right out of the box, which is why the software is so easy to use. But what this does, it kind of makes the technology too easy to use. So there's less focus and less requirements on training just to get a result. Grade schoolers could use these pieces of equipment to get a result on the analyzer screen. Does that mean they're getting the right result? Maybe not. So with that lower emphasis on training, there's less understanding, and this leads to either false positives that can lead to material mix-ups, just because people aren't necessarily understanding what they see on the screen. They're looking for a result, and if they get the result they're looking for, they don't really need to understand anything else, and they move on to the next piece. Example of this is when it comes to sample preparation. All of these are surface techniques. So if they're dirty, if there's paint, if there's any kind of coating or corrosion on the surface, that can affect your results. While it's harder to get a result on surfaces like that with libs and mobile OES, you have to make sure you do the sample prep for those. XRF is more forgiving of situations like that. So it's always going to give you a result, and it might not always be the right result. So you definitely have to be careful. Some things I'd like you to take away from today's discussion. Obviously, PMI is important. It basically verifies the structure of the world around us, the world we live in. It should be done whenever the metal changes hands in the supply chain. It's very easy to assume it's right based on the person that told you what it was, or the material test report that you saw. But as the supply chain diversifies, it's really best to make sure that the material is what you need it to be. And take a moment to understand the technology that you're using to get these results and what those results mean. Doing so will reduce a lot of headache down the road for you and your customers, and it will help us all to avoid some of the mistakes and disasters that we hear on the news every now and then. So thanks for listening to this episode of The Manufacturing Show. If Again, I'm Chris Carolyn of Metal Analysis Group. Please contact me on LinkedIn to chat PMI or anything metals. I'm happy to answer any questions or provide recommendations. If you like this episode or have a question, please join the discussion on Instagram at The Manufacturing Show. Thank you for tuning in and subscribing to The Manufacturing Show. And until next time, never stop testing your metal.